Yeah, hi everyone. I'm Deepesh Singh. I'm a second year PhD student at the University of where am I holding this? At the University of Queensland, and my PhD advisors are Austin, Peter, and Tim. And this project of unity averaging and its application, it's done with Ryan, who's a postdoc in Agropay. And I mean, before I start, I just want to like briefly mention that I've never met John in person. I mean, but in 2018, when I was a final year bachelor student back in India, I remember I wrote almost 200 emails to people asking for internships and PhDs. And I think I received like 10 to 15 replies, of which John was one. And for sure, his was the lengthiest email mentioning links to his Facebook group and whatnot. And in the end, he ended the mail saying that I look forward to your application. Good luck with that. And I think I applied to him, but he didn't take me in finally. But I think it's fine. Uh, I mean, I'm glad, and I feel like I also should like mention like Peter Rodi and Gavin are actually one of the few people here who actually like replied to him as well. So I also wanted to thank uh, them for helping me get here. Yeah. See. Okay, so the problem statement that I want to like talk about during this session is that let's say you are given access to unitaries U and UB that are in some sense easy to implement. How do you then proceed to implement an average of these two unitaries? And more importantly, why are you interested in such questions? And so in the context of what our group does is that we consider unitaries which are linear interferometers, basically UA and UB belong to USUN. And so I mean, to start with, why the reason we have been looking at this question in our group is we assume that U and UB are some approximations of some target unitary. We just want to know if the average of these two approximation unitaries are in any sense closer to their target unitaries. And so in that line, we have a bunch of papers from our group starting from 2018, where this paper actually sets up sets up this problem and tells you how to do such kind of averaging in the linear optics sense. And then basically a bunch of paper just looking at the applications of this kind of unity averaging in linear optics. And then there are like current research directions as well, where we try to incorporate the idea of averaging unitaries with different kind of encodings. And so only over Christmas break, actually, a visitor from CQT was visiting UQ, and they actually told us about a parallel research direction, which exists in the context of qubit. And so, of course, I mean, there's a paper from 2012 now, which I know of, which talks about doing Hamiltonian simulation using this idea of linear combination of unity operations, or LCU in short. And so the idea is that instead of using like equal weight sum of unitaries, you actually want to have like weights which change depending on what Hamiltonian simulation you want to do. And so there are a bunch of papers, mostly from Dominic here, that I got to know of, which talk about the applications of doing about the applications of LCU in Hamiltonian simulation. And to start off, I just wanted to like basically briefly give an overview or see what's happening to this averaging in the qubit picture. And so there's this lemma from the 2012 paper by Andrew Childs and Nathan Weeb, which talks about that given two unitaries that are acting on n qubits, let delta be some notion of distance between them, like some spectral norm of the difference between two unitaries. It puts an upper bound on the success probability of getting this linear combination of unitaries. And the proof goes as follows. It's easy to see that, for example, you compose your state psi with some ancilla qubit, and you create a superposition of your ancilla qubit. And then to implement this averaging protocol, you basically need access to these controlled unitaries. And so the light square here basically reference to like a zero controlled unitary, and the dark control here basically represents a one controlled unitary. And so as you move forward, when you apply these control unitaries, you gain access to this state. And when you again do a change of basis on the ancilla qubit, you now end up with this superposition state. And so as you can see here, like if you post select on the zero state of your ancilla qubit, you end up with a operation which is equal to the averaging operation of these two unitaries acting on your state psi. and you fail whenever you measure like your ancilla qubit in this state. And in general, sorry, that's the probability of failure. Yeah, sorry. Oh, it's same as the light Hadamard. All right, I'll change my coloring scheme next time for sure. But yeah, instead of like if you instead of wanting like an equal weight addition of these unitaries, if you want to do a weighted sum of these unitaries, instead of using a Hadamard, you can actually use some other single qubit rotation matrices instead of H. And then similarly, you will end up with this weighted sum of unitaries. And again, when you measure the one state of your ancilla qubit, you fail. And then you can also like bound the failure probabilities using the amplitude square of this term. And similarly, you can get these bounds as follows. So basically, just the amplitude square of the one term here, and then using some triangle inequality, you can just so basically this puts on how often can you get this weighted sum. And okay, so I mean, we can proceed to generalize this method and say that let W be some unitary such that it acts on a composite system of some ancilla qubits and some state psi. And with probability P, you basically end up applying some operation U on your state psi. And with probability 1 minus P, you end up on this orthogonal state. And the definition of the orthogonal state is enough to be derived from the ancilla qubit state. And so what we eventually want to do is that we want to boost up the success probability of getting this state, which is our end goal. And so, I mean, we can proceed just doing classical repetition, basically just apply this W operation order 1 by P times, and with a high enough success probability, you'll end up getting this state. But then if you don't have so many copies of psi available to you, if you only just have like one copy, you can proceed to use amplitude amplification. But then the conundrum here is that to boost the success probability of landing on this good state or the mark state in the context of Grover search, let's say, you eventually have to use the same operator. So I mean, the workaround this problem was given in this paper using this trick called amplitude amplification, OAA, which says that if the operator that you're trying to apply U is very close to a unitary, you only need reflections around the ancilla qubit and not the complete state. And so a very brief overview of the application. For example, in the context of Hamiltonian simulation, let's say you're given access to some local Hamiltonian edge acting on, let's say, like order 1 qubits, and you want to implement the unitary up to some precision epsilon. And then the algorithm for this goes as follows. So basically, you take your Hamiltonian and you rewrite it as like in the form of tensor product of polys acting on each qubit. And then basically you divide your whole unitary into some time segments, and each of these time segments can then be expanded in the Taylor series. And what you now have is your unitary, which you wanted to simulate, basically can be written as a sum of unitaries itself. And the trick is that if you have if you choose the time of evolution like I mean smart enough, what you can show that some kind of convergence can be achieved, and only a truncated version of this expansion is good enough to simulate this unitary. And so within this segment, then as you see, this is all just a sum of unitaries. You can apply the LCU trick here and use some kind of amplitude amplification to actually implement the unitary to some precision epsilon. Okay. So this was in the context of qubits, and like coming back to what we have been working on at our group. Now imagine that inside of the like what you have is this M mode interferometer where the operators for the modes evolve like this. But someone now gives you 2 unitaries, and someone asks you to like implement an average of these 2 unitaries on these modes. And so in the most easy case, this is how you do it. So basically, you start with the original modes, and you mix some ancilla modes with it. So these are like vacuum modes. So what we are averaging here is a very special case. So we are just considering like 4-mode unitaries here, let's say. And so I start with my original 4 modes, which have the index 0 in the end. And I mix them with a bunch of vacuum modes through a beam splitter. And then I do some permutations, and I send the corresponding modes to my layer of unitaries. Then I again do some permutation and then send it to the decoding step. And in the end, I do a post selection on my output modes. The idea is that if you're sending 0 photons in these like ancilla modes, and you also measure 0 photons upon post selection, what you end up doing is this averaging step. And so if you want to generalize this process, if you, instead of adding 2 unitaries, if you want to add n unitaries now, what you can do in general is that you generalize your encoding step using DFT matrices. And now you want to send in like a vacuum in the ancilla modes, and you want to measure vacuum in the output modes. And whenever you do that, you are sure that you have implemented an average of these unitaries. I mean, you can start writing out the mode evolution equations, and I mean, so I mean, just trust me on this, if you will. Uh, so what you can do is that so this is the final mode evolution equation through the like this. These are the output modes, and this is how they relate to the input modes. And the idea is that when you select your subscript R to be 0 and your subscript K prime to be 0, what it means is that you're only interested in looking at the evolution of your original modes, and you don't care about the mode evolution of these ancilla modes. And so what it means is that like you're only interested in looking at the post-selection terms where 0 photons are found on these ancilla modes. And this equation basically probabilistically now reduces to this equation. So basically, your output modes are now related to the input modes by the average of the unitaries that you have fixed in here. And an application of this is now, so what we have been looking at is like, assume that all these unitaries that you're averaging now are close to some target unitary in some sense. And when I say that they're close to some target unitary, I mean that the coefficients for their generators, like the Lie algebra generators, they are centered around the target unitary coefficients, but they also have some variance. So basically, they follow some distribution. And the question that we're asking, like, if we probabilistically get an average of these unitaries, is it a good enough approximation of the target unitaries? And to do that, like we analyze the distance between the average unitary and the target unitary, and it's just equal to half the trace norm. And then it can be upper bounded by the rank of the matrix that you're looking. And so basically what this step is doing is it's putting an upper bound on the distance between 2 unitaries as a distance, as a function of the maximum entry of the difference of the 2 unitaries. And once you have gone from a matrix picture to a single random variable picture, what you can proceed to do is like put some concentration bounds on these random variables, and not the tightest bounds, but like these are good enough to show convergence. And so basically what this equation shows is that the probability that the distance between your average unitaries and your target unitaries is greater than epsilon is upper bounded as a function of the variance of your parameters, and also the number of unitaries that you are encoding or averaging. And so basically for every epsilon, we can choose a large enough n to show that you can actually converge to the target unitary. And so in the similar, just like another application that we recently looked at is in the case of fusion gates. And so assume that you are given access to some 1D linear cluster states, and I tell you that I want to make larger cluster states out of it. So if we are working in the dual like spatial real encoding, I take my n qubits, expand them in the dual real encoding, and I apply this fusion gate, which is nothing but a layer of beam splitters, then some swap operation, another layer of beam splitters, followed by some photon detections, just single photon detections. And based on the photon measurement statistics on these on these photon detectors, 50% of the time what you end up with is a larger cluster state, and 50% of the time you fail and you basically can start again. Now, for a perfect fusion gate to work, we assume that the beam speed or reflectivities are exactly 50%. The question that we're interested in is what happens if these fusion gates are not, they don't have like reflectivities exactly 50%. And so what happens when I give you access to, let's say, some fabrication facilities making these things in bulk, and they give you n of these fusion gates, but they say that the reflectivities of these things is not exactly 50%. They follow some probability distribution, let's say, which is uniform, which is centered around 0.5, but they also have some width. And so the first question that we ask is it better to use an averaged version of these fusion gates rather than randomly picking either of these fusion gates? To show that, we again plot the trace distance between the averaged fusion gate and the perfect fusion gate as a function of the distance away from perfect reflectivity. So this point, so in your x-axis, basically your error is increasing, or you are going away from the perfect behavior of the fusion gate. So what we see is that if you don't do any encoding, like if you randomly pick just a single fusion gate out of this box and look at the distance between the perfect fusion gate and the randomly chosen fusion gate, your distance increases linearly as a function of your error, let's say. But instead, if you're choosing to take an average of the two unitaries that you have picked at random from this box, the trace distance decreases. And so the whole point is that as you keep on averaging more unitaries, just like it's almost like a central limit theorem for matrices, the distance between your average variable and the target variable keeps on decreasing. And as shown before, an explicit construction of this would just be like this. So basically, you take your 4 original modes and you mix them with a bunch of ancillary modes. You mix them through DFTs, and then you send the first mode, the first output mode of each DFT to the first fusion gate. Like these are all color coded. So the second output of all DFTs to the second fusion gates, and so on. And then you mix them again to the DFT, and then you do a post selection on these ancillary modes. So if these fusion gates are all perfect, you will never measure a photon in these ancillary modes, and it would work as before. But based on the variance of the parameters of these fusion gates and how many unitaries you have bunched in here, you will measure photons in the ancillary modes based on those parameters. And so what's the point of doing all this? What we see in the end is that if your error is increasing on the x-axis, the fidelity of the cluster state that you get if you don't do anything, if you just pick a random fusion gate and you make cluster states, this is how the red line is how the fidelity of the cluster state goes. But the success probability of getting that bad cluster state always remains 0.5 because there are no ancillary modes where your photons get lost. But instead, like if you did this averaging process, the fidelity of your cluster state improves at the cost of your decreasing success probability. And so on. So basically what you can show is that if you average your random unitaries enough number of times as a function of your variable, as a function of your variance of the parameters, you can get high enough fidelity at the cost of decreasing success probability. Just in the end, just wanted to briefly mention that like we also, I mean, I'm at UK, and so we have been talking to Andrew White's group at implementing this fusion gate averaging protocol and this Quakes photonic processor chip that he has got on loan. And so just like an overview, I just thought, so our group has mostly been, as I said, we only looked at the case of unitary averaging, where all the unitaries that you're adding are, they have the same weight. But now we found this new direction where arbitrary combinations of unitaries might also be helpful. And so only when I thought that everything was exhausted, I want to just shamelessly plug this quote of my favorite poet. And so basically what we are interested is at like what can be achieved at the intersection of these two seemingly different contexts. And that's it. Thank you.
We have plenty of time for questions.
I don't know what's the status on that, but I think Brian, who's a postdoc in the group, he has been working on some kind of similar modeling where your DFT encodings are not perfect, but you also allow some like error threshold in your encoding and decodings. And then you can also bring that inside your success probabilities. And so I don't know what's the status on that, but probably I should ask him and let you know on that.
Yep, yep, noted.
Yeah, so when you have UA and UB, they're unitary, and you take the average, but that in general will not.
Yeah, that's true.
So and so you seem to relate your success probability to the trace distance between the two unitary.
Uh, is this it? Yeah.
And so I'm just wondering if there are must be special cases where if you take the average of UA and UB, you again get unitary.
Yeah.
Now, I would expect that there your failure probability would be 0.
Yeah.
It's unitary. Is there an economic relationship between the failure probability being 0 and the average unitary of an average operator being unitary?
I mean, I don't think these are the tightest bounds, but I'm not sure if it's like I know of the one direction, but I don't think it's an if only thing. I'm not very sure of that. Yeah, I only know of one direction.
Well, I might mention if your sum of unitaries is unitary itself, then you can use a oblivious amplitude amplification and get a perfect implementation.
Yeah.
Hmm.
So that way goes just go the other way.
Well, if it's not unitary, there's always going to be something which makes it fail. Well, the oblivious amplitude amplification procedure doesn't work if it's not unitary. So it's not that it gives you something. Yeah. Yeah, yeah. I imagine so. Hmm. Okay. Do we have more questions? Yep, yep.
Yep. I mean, I don't really know since I only got to know about it in Christmas. Just 2 weeks of thinking, and the only ideas I know is like they mix LCU and some kind of amplitude amplification, which is again probabilistic in the linear optics setting. So I really don't know what new stuff like what would adding unitaries with different weights be useful for in linear optics. But it's interesting that at least there's this different branch of thought. Yeah.
Thanks for a very interesting talk. So I just thought, have you heard of quantum singular value transformation?
I'm not sure.
So this is a framework for quantum algorithms that is widely considered to be like a big breakthrough in quantum algorithms. Ike Chuang had a review article called Grand Unification of Quantum Algorithms. and it's about this. Anyway, my question is whether, but it sounds like it'll be an investigation since you haven't heard of it before. Whether this could be, whether you could have optical implementations of QSVT, because like you did LCU, and then it seems natural to consider QSVT in this framework.
I'll look into it.
So it's
Thank
just
you.
a suggestion.
Thank you.